Okay, so let's start the meeting. First of all, a warm welcome from entire Elia Group to all of you. Thank you very much for joining this information session on Elia Group's recent Roadmap to Net Zero study. With this study, actually what we try to do is to look at a decarbonized system in 2050, and for Germany it will already be there in 2045, let's say. But we try to imagine like how could such a system look like and how can it actually work. And we also try to take away some uncertainty of how such a system could function. So this morning's session is focused on Germany a little bit more. So it's the 50Hertz one. This afternoon, there will be another session that focuses more on Belgium for Elia. And maybe for privacy reasons, I would just like to let you know that this meeting is recorded and everything works fine. If everything works fine, we will make the recording available also on our website. So what's on the agenda for today? First of all, I will give you a general introduction to the study, and then we have 3 blocks of content, let's say. And after every block, we will do a short question and answer moment. So first of all, Paul will present the future energy supply and demand. Then we will go into the flexibility, and we will finish with a presentation on adequacy, with also a wrap up of the focus points that we take away from this study. And then, of course, the closing remarks. So let me give you a short presentation of the speakers of today. So I'm Jan Voet. I'm manager of System of the Future at Elia Group. So that's the department looking at the energy system beyond 2030 and how a decarbonized system could work. We also have Karsten Bakker, who works in the System of the Future department. He's a market analyst. Then we have Louis Magin, who is market and adequacy analyst at Elia Transmission Belgium. And we have Dr. Paul Namacher, who is market analyst at 50Hertz. Now for the interaction, we've actually set up a Slido. So if you follow the QR code on the screen, or if you go to slido.com and you type in the code that you see on the screen, then you will be able to introduce all your questions. And the way we would like to organize it is that per block, you introduce the questions on that block. So we will start first with future energy supply and demand. Then you can put all your questions over there. Don't forget to vote on the questions, because we will tackle in the Q&A the most popular ones first, and then the ones for which we don't have time to answer, we will come back later on. Please also introduce your name. It's always easy for us to come back to you later on if there's still an open question. Voila. And after every block, I will archive all questions so that we start with an empty Slido again for the next block. But don't forget, we will come back to the questions that we didn't answer. So I will give you a little bit more time to open the Slido and to type in the code. And maybe if you can react if it worked out, that would be fantastic. Okay, let's give it another 30 seconds and then go on. We will also put the code again in the chat later on in the meeting. So if you forgot it, you can always access it. Okay. Karsten, I think we can move on. So by now, Elia Group already has like a tradition of doing every year a study that we launch in November. So the latest study is just one in a row. So in 2018 already, we worked on a consumer-centric market design. And that's also something on which we are still working. And we recently launched a white paper on such a market design. Then in 2019, we worked on how to prepare the energy system or the electricity system towards 2030, where we introduced a new market design, flexi market model. Last year, we had a look at e-mobility and what could be the impact of a massive deployment of electric vehicles on the electricity grid. And so this year, actually, we've looked at, okay, how can we realize the Green Deal? How can we come to a carbon neutral electricity system? And I will shortly introduce a bit the framework of the study, and then I will pass the words to Paul to dive into the first block. So how did we tackle this study? So first of all, if you look on the right side of this slide, we have elaborated two distinct transformation pathways on the demand side. So an electricity-focused pathway to carbon neutrality and a molecule-focused pathway. And so we started with the 1.5 tech scenario of the European Commission. So that's the scenario that the European Commission made to come to a carbon neutral energy system in 2050. And from this, we built our two scenarios. And so in the first scenario, the electricity-focused one, we see really a high degree of electrification of end use. And this means that in this scenario, the final demand for electricity goes up by more than 70%. In the molecule-focused scenario, the electricity demand will still increase by 30%, but we see that green molecules play a more important role in the final energy demand. And so starting from these global energy systems, carbon neutral energy systems in 2050, we actually then looked at, okay, what does this mean for the electricity system? And so on the left of the slide, you see the three dimensions we have looked at. The first dimension is energy balance, future supply and demand, where we tackled questions like, will Europe have enough renewable energies in 2050 to cover all the demand? How are these renewables distributed across Europe? Should have some countries excesses, other countries deficits? The second question we looked at is flexibility. So as you will see in our scenarios, we will have more than 1,000 gigawatts of PV, for example, in 2050 in Europe. So then the question comes, okay, how can we cope with these huge fluctuations of renewable energies that we will see in the European system? And the third dimension we looked at is adequacy. And in Germany, I think that's known as the Dunkelflaute issue. How can we overcome 1 or 2 weeks with low wind and sun, and what is needed for that? So important to say, our study looked at entire Europe, so Europe 27 plus UK, Norway, and Switzerland. But then we zoomed in a little bit more on Belgium and Germany. So voilà, that's it for the intro. Now I will give the word to Paul, who will present the first part on supply and demand.
Thank you, Jan. Yeah, maybe before going to the results, let me describe you a bit in more detail how we approach these questions. So basically, there are three building blocks of our analysis. The first is the definition of these two plausible transformation pathways on the demand side, the electricity-focused one and the molecule-focused one, which you see here on the left, but also on the supply side, the analysis of renewable potential in the different European countries, and then also setting up the scenarios on the deployment for renewables on photovoltaics and wind, both on and offshore, but also then taking assumptions on other electricity generators, for example, nuclear power or biomass. And then based on these scenarios, which we developed with dedicated bottom-up scenario tools, we studied we did market simulations for the whole European continent, and there we did a lot of sensitivity analysis, mainly regarding the interconnector assumptions and the flexibility assumptions, but we'll discuss this later in this session. And the third building block is then the so-called Fourier analysis, it's really based on the time series of the fluctuating demand, but also of the fluctuating supply side in a renewable based power system. And there we analyze different time scales, short-term fluctuations, weekly fluctuations, seasonal fluctuations, and to specifically answer the questions regarding the flexibility needs of the future European electricity system. So that's our methodological approach, and based on that, we aimed to answer the questions on the three dimensions: the supply and demand, the flexibility, and the adequacy, and derived three key insights. And Carsten, when you go to the next slide, we can start now with the first key insight, which is on supply and demand. And this insight says that Europe is actually short on renewables, that it needs to achieve a net zero economy by 2050. The good news is with strong renewable expansion, there is sufficient potential to cover the direct electricity demand, even if Europe goes for deep electrification and for strong direct electrification of end use. But for the green molecules need, we will likely be reliant on imports from other continents. So renewables are really to be considered as a scarce resource and are to be used wisely and efficiently. Let me give you some more insights and details on this insight. So starting first with the demand side, Jan already said it's really a European study with a focus on Belgium and Germany, but we look at the whole European continent, also including the UK and Norway and Switzerland, who are not part of the European Union, but part of our analysis because they're an important part of the European energy system. And today they have about 14,000 terawatt hours of final energy demand. About 2/3 of it are today covered by fossil fuels. But then when we go to 2050, you see here on the left and the right the two scenarios that we developed with our modeling, with our tools. And that mainly differ in the share of electricity in the final energy demand. What you also see is that the pie in total gets smaller, so the final energy demand decreases because of efficiency. And this efficiency is actually to a large part realized by electrification, which is also the reason that in the electricity focus scenario, the pie, the overall energy demand, the overall final energy demand is much smaller because electric appliances are just much more efficient. In the middle, you see again the scenario of the European Union that Jan already mentioned, also the 1.5 TEC, which we used as a basis to calibrate our scenarios. But of course, this is only available on the European scale. So we took the overall assumptions regarding economic development, for example, population growth and so on, from that, but then really the scenario development for the different European countries and also the sectors, the variation between molecules and electricity were done in-house with our tools. And to give you some more insights, what we did there on the following slide, you see the variation. You don't see the variation of in the different sectors between molecule or electricity use. It's not that slide I meant, but yeah, maybe just to tell you that, for example, when there is a higher uncertainty in a certain sector, for example, heavy traffic, then of course the scenarios deviate more from each other, whereas electric vehicles and passenger transport, private cars, we assumed a rather large share of electric vehicles in both scenarios. So that was the final energy demand that you just saw. What you see now here on the left side of the diagram is the electricity demand. First of all, in red, the direct electricity demand, which is used to cover the final energy demand for electricity, and that's of course highest in the electricity focused scenario. But then on top of it, in the turquoise color, you see the electricity that's needed to generate the hydrogen and the green molecules that are needed to realize the two scenarios. And of course, that's much higher in the molecule scenario. And because of transformation losses, conversion losses, the difference between the two scenarios even increases compared to the final energy demand, and it amounts to 1,800 terawatt hours, which is about 3 times the electricity demand of Germany today. So it's really a high number of 400 gigawatts of offshore wind power would be needed. In addition, you know, the European target for offshore wind power by 2050, and adding another 400 gigawatts is of course not an easy task. But of course, these green molecules, they can also be produced abroad, outside of Europe, but then would have to be transported here. What you see then on the right side is the supply side, and we developed 3 scenarios on the supply side. One which assumes an acceleration of renewables by a factor of 1.5, so 50% acceleration, which is not nearly enough to cover the electricity demand in the electricity focus scenario. Maybe it's enough to cover the one in the molecules focus scenario. But then, yeah, in order to reach an efficient transformation of the energy system and of the European economy, if you want to rather go for direct electrification, you need at least an acceleration of the renewable expansion by a factor of 3. Which means that each year you have to install 3 times as many renewables as you do today, from now on until 2050. And then, yeah, an expansion times 4 would even allow us to cover the whole energy demand of Europe within Europe, but yeah, that's probably beyond beyond feasibility because of acceleration, but because also of area competition, of public acceptance. The numbers here are really enormous when you look at the 870 gigawatts of onshore wind, for example. Now let's focus a bit more on Germany. But before giving you an overview again of Europe, how is Germany situated in Europe compared to the overall European picture? And what you see here is that Germany is has a rather low renewable potential compared to their energy demand. Compared to other European countries, for example, in Scandinavia, or also at the North Sea coast, where there's really an abundance of renewables, and then that really stresses also the need for more international cooperation, for more interconnectors, because not every country is actually able, with its potential, to install the appropriate amount of renewables to cover their energy demand. Yeah, and now looking at the same diagram as for Europe, we look here at the German one at our scenarios, and yeah, here you see that with an expansion with a threefold expansion, Germany would not be able to actually cover its direct electricity demand. And in plus, you have to take into account that Germany already wants to reach climate neutrality in 2045, not in 2050. So there's even more of a need for acceleration, which you see, of course, also in the targets, in the policy targets of the new German government. So, but really, then thinking again about whether this ×4 expansion is actually possible, really see the need also to go for more international cooperation to realize such renewable expansion. So also to make use of areas that are outside the national borders, for example, as we do now at 50Hertz. With the Bornholm Energy Island project together with Denmark in order to reach this. Going then to the next slide, maybe, which gives you a summary of the supply and demand block, so to say. So yeah, based on the two scenarios we defined, we really see that direct electrification is the more efficient way to go, which is actually also reflected by current third-party studies, right? That are discussed in Germany, and the development focuses more and more on the possibilities for direct electrification and the renewable expansion need to make this possible. On a European scale, we need to accelerate the renewable expansion at least by a factor of 3. When you look at Germany, you need an even higher renewable expansion acceleration, or more imports or non-domestic resources to cover this electricity demand, which is also reflected in the third key figure here, that in our scenarios, Germany is likely to be a net importer of electricity, much more, of course, also for hydrogen and synthetic and green molecules, where we really see not a large potential for domestic generation of these fuels. Of course, there will be projects of industry to do that, but yeah, it's really about using the renewables as efficiently as possible, and then thinking about what can be imported, what can be produced locally. For Belgium, just note here, the figure is much higher. Belgium really will be short on renewables, and will need much more non-domestic resources to cover their energy demand. So much maybe on giving you an overview again on the supply and demand side, and now we're really happy to take your questions. Didn't have a look at the Slido so far. So I see one. Yeah, Jan, please.
Yeah, I think we have one question. So Paul, do you tackle it?
It's interesting to see the electricity demand to reduce so much due to improved efficiency did you have also considered rebound effect in your analysis? This increased efficiency leading to increased consumption. Yeah, the first of all, the electricity demand really increases. It almost doubles in the electricity focused scenario. Not so much in the molecule focused scenario. Maybe you meant that, and there you can also see the there are underlying assumptions on efficiency and also decrease in the, let's say, conventional use of electricity in households, for example, or in industry because of more efficient appliances. But yeah, heat pumps, electric vehicles, and so on will in total lead to a much higher electricity demand. The rebound effect is covered a bit, but really these overall assumptions on the efficiency of electric appliances, for example, they were based on the 1.5 TeC scenario, and also don't differ between the two scenarios.
Okay, so for all people in the call, feel free to ask additional questions and to use a Slido, or if you have other questions right now, feel free to intervene. No other questions? Then I think, Paul, you have been crystal clear in your presentation. Thanks for that.
Thank you.
Okay, and then let's switch to the second part on flexibility. And once again, feel free to ask questions. Yeah. Okay.
Yes, I hope everyone can see my screen, and just give a shout if it's not possible. And then let's indeed move on to the second part on flexibility. So Jan already introduced the three different blocks, and so I will go a little bit deeper into the second block of the three, and that's the flexibility part. And so before we dive more into the content, I already want to give you the key insight. And so what we see is actually that there will indeed be a lot of fluctuations in a renewable energy based system. However, what we see is that if we have a well-designed system behind it, we will be able to manage those fluctuations in an efficient way. So for seasonality, we see that a well-balanced rest mix can really already support the system a lot, removing a large part of the need for seasonal storage. Then on midterm fluctuations, we see that sharing these fluctuations across different countries, that actually there we can also have a large impact on the overall intermittency of the renewable energy. And then finally, for the daily fluctuations, what we see is there, if we have the electrification of end use combined also with digitalization, then we can also integrate a lot of these daily fluctuations, mainly coming from solar. So that's a little bit the general outline. And I propose now to dive a little bit deeper into more the technical analysis. So I think I already addressed a large part of these three elements and then the adequacy part, but I will quickly go over them also to show a little bit more what we mean with the different timescales. So for daily fluctuations, what we mean there is actually the fluctuations, like I said, coming from solar between 1 and 24 hours. So everyone knows that during the day, there is a lot of solar production, during night, a lot less, or even no solar production. So in the end, this means that we see there a daily fluctuation where we need to bridge the gap between the day and the night. A similar thing can be said for the seasonal fluctuations. So for a seasonal fluctuation, we see again with the example of solar that there is more production in the summer in comparison with the winter. So you really see that solar has a seasonal fluctuation. The same can be said for wind. Actually, wind also has a seasonal effect, but it's the inverse of solar. So for wind production, we actually see that there is more production in winter in comparison with the summer. And then in between those two fluctuations, so between the daily and seasonal fluctuations, there is also still the weekly to monthly fluctuations. These are mainly driven by wind power, where you actually see that there are weeks with high amounts of wind production and then followed by weeks with low amounts of wind production. So those are the three different timeframes that we analyzed. And then next to that, there is also still the adequacy part, which Louis will dive into in a lot more detail in the third block of this presentation. So I will today, or for now, focus on those first three blocks. And let's start with the seasonal fluctuations. I think I already explained or introduced a large part of the elements. So what we can see here on the graph is the seasonal component of solar, wind onshore, and wind offshore. And like I already mentioned, you can see that for solar, there is a higher production in summer in comparison with the production in winter, whilst for wind onshore and offshore, it's the inverse. Now, if we look at the top, there you can see two different seasonal components as well. The red line here on this graph represents the sum of the three seasonal components of the renewable energies below, and the black line itself represents the total load or electricity demand throughout the year. And so what we see actually is that if we have these three different technologies, so wind onshore, wind offshore, and solar, in parallel with the right amount of capacity installed for each of these technologies, there is actually no need for a large seasonal transfer, and there is a balance between the supply and demand. There are a couple of weeks in the beginning of the year and the end of the year where you actually have a slightly higher demand than that there is production. And so this also shows that there is sometimes a need for dispatchable generation, but these periods are really limited in time. And thus really on a seasonal level, a RES-based system can work. Then maybe when we zoom a little bit more into Germany, because this was on the European level, maybe before I go to the next slide, what I also wanted to mention still was the fact that in this analysis, we focused on the electricity scenario, so the electricity demand, then combined it with the supply times 3, which Paul also introduced in the previous part of the presentation. But so now let's dive a little bit more into Germany itself. And what's interesting here to see is that Paul already mentioned it, Germany will still need some amount of imports or non-domestic energy supply in order to be able to cover their full electricity demand. But when we look at the different technologies, we actually see that there is a nice division between 2/3 of wind power and 1/3 of solar power. So it's really what we see based on those seasonal fluctuations, a very good setup in order to limit the difference between the production in summer and in winter. However, this also means that the wind power or the wind onshore, so the 30% here defined, will also need to be developed to that extent. Would this not be feasible? Then there should be more a shift towards the wind offshore to keep this positive seasonal effect. However, there really needs to remain this high ambition for wind onshore, and the focus should really be there to be able to develop this further. Why exactly? Well, when we look at this slide, so the next one, what we can see is the impact of having a different setup of renewable energy for the German case. So here on the left side, what you can see again is the base case. So like I explained, what we took here is the electricity supply or the electricity transformation pathway, sorry, with the ×3 RES deployment. As you can see, first of all, Germany is not completely supplied with energy, so there is still a slight gap. So there is on average 10 gigawatt, which still needs to be produced outside of its own borders. And on top of that, you can also see that there is still some seasonal fluctuations because of a balance between wind onshore, wind offshore, and solar, which is not the most optimal case. And then based on that, we made actually two differentiations. One case where this gap, those 10 gigawatts were supplied with wind offshore, so fully wind offshore from outside of the German zone. And the second case where part of the wind offshore is supplied, or the gap, sorry, is still supplied by wind offshore, so 3 gigawatts, but a large part, or the largest part, is supplied by solar. So really increasing the overall solar production within the German borders. And on a seasonal level, you can really see the differentiation between the two. So in a case where we add mainly wind offshore to the mix, you can see that the fluctuations are relatively limited, and thus there's not really a season-long flexibility need that is introduced into the electricity system. However, if we put the focus more on the development of solar, what we can see there is that there is a large seasonal spread which is being introduced. So it almost doubles in comparison with the base case. So there you see that then more the need for a seasonal flexibility would be needed. So what does this mean? Well, in short, really pay attention when developing the mix, because having a good balance between wind onshore, offshore, and solar actually means that you can reduce this seasonal transfer and thus also the energy losses associated with that. So that's the part for the seasonal fluctuations. Let's now move on to the medium-term fluctuations. So what we analyzed here was a way to actually mitigate those medium-term fluctuations, like I said, mainly driven by the production of wind. And this analysis, unfortunately, we only focused this one on Belgium, but the similar trend can be seen for Germany as well. And so what we did here was we took Belgium as a reference area and analyzed how often there is wind production in Belgium at the same time as the close neighbors that you can see here. And it might be a little bit counterintuitive, but the higher the number is, actually the worse the situation is, because that means that there is a lot of wind production at the same time between those two countries. So for example, it means that there is often production in Belgium at the same time as that there is in the south of the UK or in the Netherlands. However, what we see then when we're moving a little bit further away from Belgium, so looking at Denmark, for example, Norway, even also the north of the UK, there we see actually that there's a decorrelation happening. So this means that there is no production at the same time between Belgium and those other countries, or at least a lot less. And so what we see is that by interconnecting these countries, we can actually share the fluctuations which are inherent to the production of wind, and thus limit the overall flexibility need that there is in the electricity system. What does this mean in terms of numbers? Well, if we compare the situation where Belgium is really analyzed as an island in comparison to a EU interconnected system, we see that we can almost halve the need for flexibility coming from the production of wind, so these medium-term fluctuations. So also there, when having a intelligently developed or a well-designed system, you can already mitigate a large part of these fluctuations. Then let's go to the final one of the three timeframes, and these are the daily fluctuations. And I already introduced it a little bit, but what you can see for those daily fluctuations, that they are mainly driven by the production of solar energy. And what we took here is a typical week in summer, where you can see that there is, because of the high production of or the high production of solar, that there is a high production during the day. So the yellow area here represents solar production during day, and that there is no production during the night. What you can also see is that then there is an activation of the flexibility, which is the red part. So the flexibility is consuming energy during the day when there is also a high amount of solar production, and then releasing this energy back to the system when there is a lower amount of solar production or no amount of solar production during the night, actually transferring this energy. So that's the principle behind it. However, what does this now mean in more detail? Well, what we did here was do an analysis specifically focused on Germany to see, okay, between two different levels of flexibility, so having either a low amount of flexibility in the energy system or a high amount of flexibility in the energy system. What does this now mean? And so on the left side, you can see the low flex scenario, where there is still a high amount of days where there is over and under supply. Well, what does this mean? This means that there are days where you have too much production of, for example, solar energy during the day, but you aren't able to transfer this sufficiently. So it means that during the night, there is still undersupply, and so there is need to supply or to produce additional energy based on other resources. When we now move to a high flexibility scenario, so where there's a lot more flexibility in the electricity system, you can see that those 44% days with with over and under supply almost completely disappear. So there are only 4% of those days left. And so you see that actually by introducing this flexibility, we can really help the electricity system and have a lot of reduce these days with over and under supply significantly. This of course means that they are shifted either to the energy not supplied or to the energy spilled part, but overall the electricity system itself will work a lot more efficiently. So those are the three different timeframes that we investigated. I hope that was a little bit clear, but if not, please feel free to ask any questions that you want.
Thank you, Karsten. There was one question in the Slido, but it's already answered. It was on slide 18, whether the renewable shown was for entire Europe. I think this was the case, and it is indeed a seasonal component. So this is the fluctuations with the duration between 1 month and 12 months. So that's why the graph isn't that spiky. It's really the long-term fluctuations that we've shown. As there are no other questions in the Slido, I would, there's another one. I will share my screen so that we can look at it. So the question is, how does energy not served rises with higher flexibility, or what is the number of total days that you identified?
Yes, no, good question. So yeah, I will maybe go back to my presentation then, if that's okay, because it's a little bit easier to explain it with the numbers behind it. And so normally you should be able to see my screen. So indeed, the amount of energy not supplied increases. There are actually two reasons for this. So first of all, what we do is we reduce the days with over and under supply. So when we are doing this, it means that there are three options. Either there is only oversupply left, either there is only undersupply left, or there is no more over and no undersupply left. So we'll go to the green category. And so this explains that when a day has over and undersupply, and you then integrate all that energy that's available, but it's still not enough to resolve all your undersupply, it actually means that it's moved towards the ENS part, so to the 45% part. Now, the reason that there is still 45% there is because of, first of all, the Germany itself is still in undersupply. So it means we did this analysis on Germany where it is on average 10 gigawatts short. So it means that there are still a lot of days left where there is not enough energy available for Germany to supply its full energy demand. And then secondly, what we also see is that, or this analysis is also done on a daily basis. So it means that if there is a day where there is just 1 hour with undersupply, it also gets put into that category, which then could be easily solved by having, for example, some dispatchable capacity available. I think that answers the question.
To elaborate a bit further on that, the graph that's shown here is for the IOSN 2040 grid that we took into account. So that's a limited grid, not yet a copper plate. And so probably it's underdimensioned for the 2050 situation. And I think later on in the presentation, Louis will show also the impact. What if you go to a higher level of interconnection, and then you see that the amount of days with energy not served will decrease quite a bit. So interconnection is also a very important one in this one. And secondly, the graph shown here is before addition of any dispatchable capacities to the system. So in the third block, you will see what happens also on the adequacy part. So in our final simulations, let's be clear, there is no energy not served, or the energy not served is in line with the policies that are followed in the different countries. Okay, then there is...
Yes, indeed. Thank you.
Another question, I think Louis, that's probably Louis or Hannes, another expert in the call of Elia Group. It's for you. What was the base of your RES availability assessment, PECD? Have you considered the impact of climate change on RES availability and load?
Yes, so for the RES availability, we took into account indeed the PECD database from NSOE. But we considered a new methodology with the detrended climate database from NSOE, which mitigates the effect of the later years of the database from NSOE.
And then the second part was on the effect of climate change on RES availability and load.
Yeah, but so for this we took it into account via this detrended climate database from NSOE, and yeah, we mainly assess the impact of the higher electrification of the on the load, and the climate database in order to assess really the thermosensitivity of the profile.
Okay, thank you. Any other questions in the call? No. Okay, then thank you very much, Karsten. Then I think we can now move to the third part of the presentation, which is on adequacy, and it's Louis that will present this part. Go ahead.
Thanks, Jan. Yeah, so indeed, this third insight will be dedicated on adequacy. So to remind a bit the process, so in the first insight, we defined the different transformation pathway, so basically the demand and the supply data. In the second insight, we use our different tools, the market simulations, the Fourier analysis, in order to assess the impact of the flexibility mean. And so this third insight consists in an adequacy assessment with different level of flexibility and also the impact of different grid configuration. So what do we mean with an adequacy assessments? We speak about an iterative process which consists in adding some backup capacity in different countries until we reach a global adequate system at European level. So it's important to say that we are speaking about backup capacity, but we do not make any choice on the technology to cover this need. So there is different climate neutral technology which can fulfill this need, such as hydrogen fired gas turbine, fuel cells, biomass, and so on. There is some technologies which are already mature, but others are still under development. So we don't make any assumption on this in this assessment. So first, regarding the we will try to identify the need for backup capacity. So it's on the next slide. So again, we take as an example the load filling that we have for a typical summer period in Belgium. So we look at elect demand scenario with the BRU times 3 supply risk, so a moderate risk supply, the grid IRSN plus, so a limited grid, and a high level of flexibility. So based on this load filling, what we observe is that during the periods with low resin feed, so basically no solar generation produced and a limited amount of wind, we have also a limited contribution of the imports, but also the flexibility provides a more limited p-value, which limits the amount of energy available. And so it means that during two periods, which are in purple on the graph, there is a need for backup capacity in order to ensure an adequate system. The identification of the need, we can also show it on a different way. So if we go to next slide, by taking the same approach that was presented by Karsten in the second insight. So again, we look at the distribution of days across the year in Germany. So with the, in this case, we have high flexibility and the copper plate. So we are an ideal system, and we look and we split the days in 4 categories depending on if there is at least 1 hour of under or oversupply during the year. So what we see here is that with a high level of flexibility and with a strong European interconnection, we reduce all the intraday variation. So the orange part is equal to 0, and we also solve a part of the weekly variations. However, there is still some days with undersupply, which are on the left of the graph. So we see that during 90% of the days, there is still a need. There is still undersupply, and that's why some backup capacity will be needed in order to cover these periods with undersupply. So that was for the identification of the need. On the next one, we based on the Fourier analysis, we also try to see when does the scarcity situation occurs. So indeed, we have a system which is mainly driven by the rest generation, and so it means that the scarcity situation are mainly linked to prolonged situation of low rest generation. So if we look on the left part, we see the occurrences of low wind generation events on average per year in Germany, and we see that the long events mainly happen for onshore wind. So what does it mean for Germany? It's that having a large share of offshore wind in the mix will reduce the occurrences and length of low rest events in the German power system. On the right part of this slide, we look at the occurrences of the total low rest generation events on average. And if we look at the countries isolated, so for Belgium and Germany on their own, we see that there is still a certain gap that need to be fulfilled by backup capacity to cover these different events that we show on the country isolated. But what we also see is that if we look at the entire Europe with all the system being a copper plate, we see that the long periods of low rest in feed rarely occur simultaneously across the entire Europe. So there is a kind of pooling effect, which lead to a limited number of low rest events longer than 4 days, which means that with strong interconnection across Europe, the extreme events can be balanced, and that it will, of course, reduce the need of the backup capacity. So now that we identify that there is this need, we try to quantify it. So in order to do this, again, we take a reference scenario. So the scenario is the elect demand, so a high degree of electrification, and the BI times 3 rest supply scenario. So yeah, voila. And we took into account different sensitivities. One sensitivity is on the level of flexibility, with a scenario with low flexibility, another one with the high flexibility, and another one regarding the grid. So one with a more limited grid, and another one with all the links set to infinite. So Europe considered as a copper plate. So what we see is that with a low level of flexibility and this limited grid, there is a need for backup capacity for about 400 gigawatt, and that this need can already be reduced by 100 gigawatt if we add a high level of end user flexibility to the system. And this amount of installed capacity can even decrease by 60 gigawatt if we have strong European interconnection in the system. So in total, it means that we can go from 400 gigawatt to more or less 240, so a decrease of 40% by considering both a strong European interconnection and high end user flexibility. And we can also do the same kind of analysis by looking at country level. And for this, for Germany, we see that the estimated required backup capacity would be equal between 40 and 70 gigawatts, depending on of the scenario considered. Then the last part regarding this backup capacity is really to look how often they will be running. So for this, we have this graph with the electricity generation from this backup capacity. So on this particular graph, we took into account a scenario with the high flexibility and the limited grid. And for the backup generation at European level. So we have in dotted point the average values of the generation of this backup capacity across all the Monte Carlo years that we considered, and the blue bars represent the different percentiles, so the P10, P40, P60, and P90 for the generation of those backup capacity. So what we observe is that it's really linked to the residual load that we see, so to the load minus the rest in feed, and so the need for backup capacity is more limited in summer and during interseason, and is still quite important in winter. So basically from November to February. But for this scenario, we also have to know that the grid is limited, which means that the countries which are structurally in undersupply cannot import all the energy that they need because of the grid, which is in this case a constraint to the system. But it means that with the right amount of European interconnections, the amount of backup capacity and also the running hours will decrease. So as a conclusion for this part on adequacy, so we see that first there is a significant capacity need, but with limited running hours, which would lead to investment in technology with a priori low capex cost. And a second conclusion is that there is a balanced rest mix, as already introduced by Karsten in the second insight, with sufficient level of interconnection and with a high flexibility of the end users from EV, heat pumps, and etc. It can reduce significantly the need of this backup capacity. So that was it for this point.
Thank you very much, Louis. So now I will shortly present the conclusions or focus points that we take out of the key insights on energy balance, flexibility, and adequacy. So if you go to the next slide. So for us, the focus points in the study is really where we need to put the focus on during the upcoming decade. And a first conclusion for us is that renewables are scarce. I think that was shown in the beginning by Paul. So in Europe, even if we speed up 3 times, we will not have enough renewables to cover the entire energy demand. So to cover direct and indirect electrification, which makes actually that it's very important that all the countries in Europe start to work together. So countries with an excess of renewable potential and countries with a deficit of renewable potential should work together and should make sure that renewables are exchanged between themselves. A second conclusion we draw from this is that it's important to make sure that there are efficient arrangements with UK and Norway, even if they are not fully part of Europe. Looking at the offshore potential in these two countries, they will be very important for us to make sure that we can come to an efficient system. And then a third conclusion on efficient use of renewables is that knowing that renewables will be scarce and that we, in a 3 times accelerated scenario, we will only have enough renewables to cover direct electricity demand, it's also important to start to look for a global market for molecules, because typically molecules can be imported more easily from other continents than electrons over such large distances. And this is especially the case for Belgium and Germany, which I think Paul also showed on the map that they are short on renewables. So that means that probably a large share of their green molecules will need to be imported from other countries, meaning that we should also start to investigate whether Belgium and Germany couldn't become like the green molecule hubs of Europe. A second focus point that we derive from this is that accelerating RES deployment with a factor 3 will not be easy. It is a major challenge and it will not come from itself. So first of all, we believe that we should halve permitting times. Today, permitting can take up to, if you look at infrastructure, up to 8 or even 10 years, worst case. So it's clear if we cannot accelerate this process, then we will probably not be able to get to this business as usual ×3 scenario for RES deployment. Also looking at RES deployment, it's important also along the way towards 2050 to keep the right mix of renewables. So as Karsten has shown in the flexibility part, a right mix of sun and wind makes sure that there is no structural mismatch between demand and supply on a seasonal level. And that's actually quite important. And what does that actually mean? Probably solar PV is the easiest technology to scale up. However, if you look to wind, onshore wind, there are issues of public acceptance, permitting issues. So we really need to make sure that onshore wind follows the planned track towards 2050. And if you look to offshore, it's important to make sure that sufficient space will be foreseen offshore to make sure that we can reach this target of 410 gigawatts of offshore wind in Europe. And then a final aspect of this second focus point is that in terms of infrastructure, we also believe that we need to start to look to leading infrastructure, which means that the infrastructure should be ready to connect further renewables, and that we don't need always to wait to a renewable project to build infrastructure, because in that case, we will have the risk that transmission will be a bottleneck in realizing this massive RES deployment. Then the third focus point we have is on electrification and its importance. So we believe that electrification is like a win-win and should be incentivized. First of all, as was shown by Paul in the beginning of the presentation, electrified end use is typically more efficient than molecule-based end use. So if you look at EVs, if you look at heat pumps, we see that they consume less energy, which actually means that if you electrify these end uses, you can go faster in the decarbonization, because you can decarbonize more end use with fewer renewables, which, as already told before, are a scarce good. And secondly, as was shown in the part of flexibility, if you electrify this end use, it becomes more flexible. And this flexibility is important to allow the further integration of renewables. So if you want to integrate a lot of PV with a lot of daily fluctuations, it's also important that we have flexible end use like EVs, heat pumps that consume electricity in a smart way, let's say. And for this, we need digitalization and we need a new market design. And Elia Group is quite active on that, because we published a white paper on such a consumer-centric market design, which can be found on our website. And then the final focus point is that as renewables will be scarce, as there will be huge ramp up of green molecules also over the upcoming decade, we believe that it's important to use these green molecules first in sectors where direct electrification is not an option. So to make sure that the green hydrogen is first used in the sector where it provides most value. And secondly, we also believe that for the local production of green molecules, we should always make sure that, first of all, sufficient renewables are available to cover direct electricity demand before considering massive production of green molecules. Why? Because typically green molecules can be imported more easily across large distances. So for us, these are more or less the conclusions of our study in terms of focus points. And so I now suggest that we go to the questions in the Slido. Let me share my screen.
Okay, so the first question, what kind of scenarios are used to estimate scarcity situations? So as mentioned, we use different scenarios to estimate the scarcity situations. So we start from a scenario with a high degree of electrification and the Bearut times 3 rest supply, and then we look at different level of flexibility and different level of different grid configuration, and for every sensitivity, we make this analysis of the scarcity situations, and we did this adequacy assessments to reach the amount of backup capacity which is required at European level. For the second question, are tail risk events taken into account? Oh, okay. But for the second part of the question, all the scarcity events are the results of the results of the market simulations. So it means that it's really the scarcity situation after after taking into account the correct contribution of the grid and the flexibility. Okay, so I don't know if it's on.
Louis, what is the risk of ANS that we take in the simulations? I think it's really the tail that we also consider. It's 99.97% or something like that.
Yeah, we consider that all countries must be compliant with a 3 hours of Lowley criteria, which is the basic for the adequacy assessment at European level.
Okay.
So for what kind of technology do you consider as backup capacity? For this, indeed, we consider that a certain amount of dispatchable capacity are needed in the system in order to make it adequate. But as mentioned in the beginning of the presentation, there is no choice of the technology which I really need to occur today, because we consider that behind this concept of backup capacity, there can be different climate neutral technologies which can contribute to cover this mean, and which can be hydrogen fired gas turbine fuel cells, but it can be different technologies and even new technologies as a result of technological breakthrough on the way to 2050, for example.
I think on this one, we also believe that in the upcoming years, it will be mostly existing and new thermal capacities that will take on this role of backup capacity. Then we believe it's very important to speed up renewable integration, because it will reduce the amount of running hours of these backup capacities, and hence reduce a lot their greenhouse gas emissions. And then only in a second stage, when we are there, and that's not in the upcoming, let's say, 1 to 5 years, only when we then need to decarbonize the backup capacity itself, we believe that there are multiple technologies, but there might still be breakthroughs by that point in time, let's say. So first of all, it's really the massive deployment of renewables where we need to focus on to reduce greenhouse gas emissions.
Yes.
Okay, then the next question, you mentioned the relevance of UK and Norway. Will Switzerland not be relevant in your considerations? Yes, it is. We also simulated Switzerland in our European model. We focus on UK and Norway because they have massive offshore volumes available. I think more than 30% of the offshore in the European region is either from UK or Norway. And then if we consider these volumes, then we see that we have just enough renewables in the business as usual ×3 scenario to cover direct electricity demand. So that's why we emphasize really that good relations with UK and Norway for renewables are important. Of course, that doesn't mean that Switzerland is not important, but in terms of renewable potential, I think UK and Norway are, yeah, just massive.
Okay, then how likely do you consider, do you think it's a copper plate-like grid in Europe? Yeah, so of course, considering a copper plate for Europe is a really theoretical exercise. So also in the report, what we try to do is to quantify or give an idea of what would be the flows between the different zones of the country. So this is something that you can see on figure 14 of the report, which is available on Elia website. And what we from this analysis, what we show is that there is a potential for additional interconnection, basically to integrate the wind generation potential from basically the Nordics and UK. So the production which is produced in the North Sea and in the Baltic Sea, but yeah, which is really a theoretical a theoretical case. And then for the second part, have you looked at economic trade-off between backup capacity, flexibility, and grid expansion? So for this, there is no cost assessments which has been performed on our scenarios. Mainly because there is a high degree of uncertainties regarding the cost of the different technologies, of what we consider as cost for the different flexibility means, because behind the flexibility means it's basically the electric vehicles, the heat pumps, and so on. There were no trade-off between the different these different parameters.
I think to complete on that, we actually did the calculations for a more limited grid. So the grid in TYNDP, IOSM 2040, and the copper plate. So I think the results of both scenarios, they are shown. And then I think it's up to the reader to make this kind of considerations. But as Louis told, the degree of uncertainty towards 2050 is so high that it's very difficult to make this trade-off at this stage. So it's better to work with different scenarios than to try to calculate the optimum with a very uncertain input.
Okay, and then for the last one, are there any trends regarding the production of renewable energy from biomass? For this, we took into account two things. On the demand side, we took into account the target set at European level with the value from the 1.5 TEC as a reference. And on the supply side, the amount of biomass generation in the different countries are based on the on the scenarios from the TNDP and are assumed to be fixed in the different waste supply scenarios. So we make some variation regarding the solar PV, the wind onshore, the wind offshore, but for biomass, among others, the installed capacity available is considered as a fixed value.
Okay. Then are there any other questions, remarks, appreciations of the study? Feel free to intervene. If not, I will move towards the closing remarks already. So a bit ahead of schedule. We expected some more questions, let's say. So any other question? No. Then I think, Kersen, can you go back to the
Yes, already
presentation?
there.
So voilà, then before we finish, already during the introduction, I said that Elia Group has this yearly tradition of doing a study. And so we'd also like to announce here what will be the topic of next year's study. And we are going to focus on decarbonization of industry. Why do we do this? Because we have seen that in the 2050 scenarios, industry and in particular their degree of electrification or use of green molecules will be very important in the future, also for the grid build out. And so that's a topic where we want to get more mature and to look into that together with industrial parties. And for this, we'll focus on 3 segments. So the first segment would be energy intensive industries. So what do they need for the energy transition? The second segment would be data centers. What can they do to become carbon neutral? And then we'll also look into service and logistics centers. So those are more like the companies with distributed service centers, like how can they optimize their total energy consumption and become carbon neutral. So by this, a request, if you would like to be involved in this study, please contact us. The email addresses are here below. On the slide, and so looking forward to work together with some of you then over the upcoming year. I also see another question. What are your next steps in terms of advocating your findings in public and politics? So of course, both in Belgium and Germany, we will use this study to also show people how a decarbonized system can work. So we will continue our advocacy on the basis of this study and make sure that policymakers get to know our focus points and what is important to move towards decarbonization. So that's something we will do. And then on the final slides, maybe before we finish, we would also like to thank all the parties that have given feedback and contributed to this study. This morning I counted them. It's almost 50 parties, I think, that we have contacted who gave us feedback, etc., on the scenarios, who contributed, who delivered quotes. So there's only a few of them on this slide, but big thanks to all of them. Voila. And then also a big thanks for you to join this session. The recording will be shared online. The study is available online. And should you have further questions, don't hesitate to come back to us. And then we are more than happy to answer. So voila. Have a nice rest of the day then. See you. Bye.
Thanks, everyone. Bye.